have Siddharth Muthukrishnan talking about unpacking or complementarity from Pittsburgh agents.
Okay, thank you. So this is a paper that's recently been accepted in this journal, the British Journal for the Philosophy of Science. So you can look up the reference, and the preprint addresses are there as well for further information. So the context for black hole complementarity is the black hole information paradox. I don't need to tell this audience that this is a central problem in modern theoretical physics, and black hole complementarity is a family of responses to the information paradox. So the goal of this talk is to address this question: how should we understand black hole complementarity? So the setup here is, of course, an evaporating black hole. So this is, of course, a stylized Penrose diagram. We don't know exactly what the Penrose diagram for a evaporating black hole is going to look like, but this is a useful first approximation. So we have three sort of representative slices here: a pre-formation slice, a slice during evaporation, and a post-evaporation slice. The version of the paradox, the information paradox that we're going to be interested in, is what has been called by some, most recently by David Wallace, as the page time paradox. At this point, it's worth sort of taking a moment to distinguish this from the paradox, which is often presented in popular venues, but also in some technical venues, which is called the total evaporation paradox. So the total evaporation paradox can be roughly stated as follows, which is like, so data on the evaporation slice, and none of that data is going to be, some of that data is not going to be available in the post-evaporation slice because it's hidden behind the horizon, and then there's a singularity, and the suggestion is that you have a non-unitarity, and that's kind of maybe a paradox because you think, well, quantum mechanics is unitary. The problem with that way of stating the paradox is that it's not very pressing, because in between the evaporation slice and the post-evaporation slice, you have a singularity. And you might think, well, at least on many ways of thinking about a singularity, it's basically a placeholder for future physics that we don't yet have a good handle on. So that's part of the motivation for some of the solutions like remnants or thunderbolts. Or another way to state the non-pressingness of this paradox is to just look at the space-time here and notice that it's not globally hyperbolic. And you might think, well, we only expect unitarity to hold in globally hyperbolic spacetimes. This is not a globally hyperbolic spacetime. What are you worried about? So we're not going to deal with that way of thinking about the paradox. We're going to instead deal with this way of thinking about the paradox, which not only has the feature of being statable in a regime where we believe our physics is under good theoretical control, but moreover, is the way in which black hole complementarity thinks about the paradox and the way modern physicists have been sort of working with the paradox. So here we have three statements, and that are going to form an inconsistent triad. First statement is, of course, that black hole evaporation is unitary. The second statement is slightly more involved, which is that the black hole is just like any ordinary thermal statistical object, in that the von Neumann entropy of the von Neumann entropy, the fine grain entropy, the Gibbs entropy of the black hole is bounded about by its Boltzmann entropy, coarse grain entropy, Bekenstein-Hawking entropy. Right? So just as any for ordinary statistical objects, the Gibbs entropy is always bounded about by the Boltzmann entropy. The same is true for a black hole. And the third premise that's going to be from the contradiction is that Hawking radiation is perfectly thermal throughout evaporation. So let's see how these three things together bring out a paradox. The picture here is fairly standard, but let me just go through it. So on the vertical axis, we have the black hole entropy. On the horizontal axis, we have time. So as the black hole evaporates away, we have the area of the black hole decreasing. And so this means that the Bekenstein-Hawking entropy of the black hole is decreasing. Now, if the black hole evaporation is unitary, and if the radiation were always thermal, then it must be the case that the phenomenon entropy of the black hole is increasing monotonically. This is because the radiation entropy must be equal to black hole entropy, which follows from the fact that for a pure bipartite system, the entanglement entropies of the bipartitions are equal. On the other hand, if it's evaporating unitarily and it's a quantum statistical object, then it must be the case that the phenomenon entropy of the black hole is bounded above by its Bekenstein-Hawking entropy. And so it must be the case that the entropy curve can't keep increasing, it has to start decreasing at some point. And obviously, the entropy can't do both things at the same time, and so you have a contradiction. And Don Page argued that this turnaround point will roughly be almost exactly halfway through the evaporation of the black hole. The intuition for this is fairly straightforward, so you can imagine, as a stylized scenario, you can imagine that the black hole forms from the collapse of a large collection of maximally entangled pairs, and imagine that the black hole radiates a random particle at a time. And so initially, it'll be very unlikely that the entangled partners of the radiated pair is already available in the radiation. But halfway through, it becomes more likely than not that the radiation has the partners paired up. And so the radiation starts purifying. And so over time, the entropy is less decreasing. That's just to have a stylized picture. That's not suggesting that it's a mechanism for an actual black hole.
When you say the evaporation is unitary, and black hole is statistical mechanical, does that mean it's irreducibly statistical mechanical? That is, I mean, you could have something that was described statistical mechanically, but that was, I don't know, that was due to our ignorance, and it had an underlying unitary representation. But you're saying something stronger than that there. You're saying, what if it's only describable statistically?
No, I don't need something stronger. I think you can. So, as such, in foundations of StatMech, I'm not particularly committed to the idea that the entropies quantify our ignorance. But I think if you prefer that way of thinking, I don't think there's any fundamental barrier. In fact, I do think that this premise suggested, along with that premise, that there is a perfectly unitary description available at some level if we wanted to. Yeah. Okay. By the way, I'm not going to argue for those three premises. I've put up some references there. They've been argued in detail. The evidence for these premises have been collected in exhaustive detail in these papers by David Wallace. We can talk about it if we want, but that's not going to be the focus of my presentation here. Okay, so we have a contradiction. So what do we do with the inconsistency? So obviously the thought is that you should give up one or more of your commitments. But science often goes on even when you don't, even when you have an inconsistency. So there's a nice book by the philosopher of science, Peter Vickers, called Understanding Inconsistent Science, where he collects many examples in the history of physics where there was an inconsistency in the theory, but the sort of practice of the theory went along just fine for a while. An example is that might sort of a little provocative is that some people think of the measurement problem of quantum mechanics as essentially an inconsistency within the theory. So someone might say, well, look, your theory has two dynamical rules. One of them is Schrodinger evolution. The other is the one given by the measurement postulate. And you're saying both of them are occurring. That can't possibly be right. And in any given scenario, we have good reasons to believe that both of them is applicable, or there are scenarios for which we can imagine both of them are applicable. I'm not committed to that particular way of thinking about the measurement problem, but I'm just flagging that, quantum mechanics is an example of a theory that possibly went on just fine, even in the face of an inconsistency. So why is that okay in some cases? Well, because there aren't any empirically observable contradictions from that inconsistency. So in order to understand which one of these commitments we need to give up, or whether we need to give up any of our commitments at all, we need to understand whether there are empirically observable contradictions from the physics of an evaporating black hole. So here's an initial attempt at getting an empirically observable contradiction. So, we had these two entropy curves, and you might think, well, why not simply look and see which one of these entropy curves, if it's the Hawking curve or if it's the Page curve, and then if we see that it's the Hawking curve, then we know that we have to give up the statistical mechanical or the unitary premise, or if it's the Page curve, then we know that we have to give up the thermality premise. So how would you go about doing that? Well, you can imagine Bob hovering outside the black hole. So always the person outside the black hole is going to be Bob. So Bob is the spectacular experimentalist. He has built like a huge Dyson sphere around the black hole. He's collecting every quantum of radiation coming from it, including all the gravitons. And he's just going to check and see whether, well, hey, is it going to be the Hawking curve or the Page curve? And then we'll have an empirical measurement of the inconsistency. Well, the issue with that is that, firstly, entropy is not an observable in quantum mechanics, right? So you can't. So there is no Hermitian operator which has entropy as its eigenstates, precisely because the eigenstates of Hermitian operators are pure states, and so entropy is 0. And so you can't just measure entropy. You might think, well, okay, we don't measure entropy directly; we measure some other observables that can help us distinguish between these two curves. And well, then that's where one of the, so you're going to run into many problems, but just to flag one problem that you might have. So some of the more popular models of black hole dynamics treat the black hole as a random unitary model. That is, after some period of evolution, the black hole and radiation state are going to be indistinguishable by sort of some finite measurements on subsystems from a random state in the Hilbert space. And that'll be enough for us to prevent us from distinguishing between the two curves, because from outside measurements, we can't really tell whether our system is perfectly thermal or simply is a pure state that has been randomly selected but looks thermal on measurements. You can make that mathematically precise. Okay, so this is where black hole complementarity has started coming in. So let me put up what I got. So I'm going to identify two principles of black hole complementarity. The first principle is what I'm calling operational complementarity. And essentially it says that, you're always going to have some problem like this. You're always going to be thwarted in attempting to isolate the contradiction into some sort of empirical issue. So my statement is that no experiment attempting to create the observation of a direct contradiction of the rules of quantum mechanics by single observers near or in black hole will succeed. So this is sort of a distillation of statements that you can find in many places in the literature. I've just put up some references here. I think let me just emphasize here that by operational, what I mean is that this principle makes reference to observers. So I want to sort of flag that this isn't quite the notion of operationalization that you find, for example, in information theory, where to operationalize a quantity is to specify some task for which to operationalize a quantity is to specify some task for which that quantity quantifies the efficiency of that task. So for example, Shannon entropy quantifies how efficiently you can compress a sequence of messages. Also, the another sort of point to distinguish here is a notion of operationalism that comes from Percy Bridgman, who was, I guess, actually a physicist and philosopher here back in the early part of the 20th century, who gave an account of the meaning of physical quantities in terms of what measurements you can make in order to measure that quantity. So these are all related concepts, but I want to sort of flag that the one that's operative in this discussion is one that is about whether your principle makes reference to observers or not. I'm not going to unpack the relations between those. It's a different project. Another point to highlight here is the question of what we mean by an observer here. So obviously I don't mean a human, because that would be too parochial. But what I mean is some sort of measuring device that we can use to measure, collect, and manage the quantum data that you might encounter when you're dealing with a black hole evaporation. So I'm not going to make many restrictions or definitions of an observer here, but one point that's relevant and worth flagging here is that I'm going to restrict our observers in a way that they can only probe or control physics that's above the Planck scale, so above the Planck length scale, right, or below the Planck energy scale. Why? So there are a couple of ways to see this. One reason is that it's one way of motivating this is to argue that it's a kind of a provisional restriction. So that is, we don't have a very good conception of what observers are about at the Planck scale. So an analogy here might be helpful. So if you think about, let's say you have a principle, you do have a principle which restricts you from building perpetual motion machines that are energy conserving. So these are sort of energy conserving perpetual motion machines. So now you can imagine like a Maxwell's demon type observer who can manipulate microphysical degrees of freedom to get around that barrier. Now, whether or not Maxwell demons observers are possible or not is going to depend on the details of microphysics, right? Whether you can continue to intervene on molecules without building up an entropy constant background, that's not something that you can analyze without some understanding of microphysics. And indeed, this is the way Maxwell himself thought of the second law. He thought, well, it's a law that's contingent on the capabilities of microphysically constituted observers. And in a sense, he used the demon to illustrate this point. So it's similar here. So if we don't really know what's going on in the Planck scale, so it makes sense for us to restrict our observers in a way that they can't manipulate those degrees of freedom. Similarly, you have sorry, nothing wrong. Another point to emphasize here is that the space-time paradox was pressing, like I made this contrast between the space-time paradox and the total evaporation paradox, and that was a useful paradox to focus on precisely because it's stated in a regime which doesn't make appeal to Planck scale physics. So it's reasonable to try and restrict the kinds of responses that you construct to the same regime in which the paradox was. But that's why I'm going to say that our observers can't probe the Planck scale.
So I have a question here.
Yeah, please.
So I understand the kind of the statement that this observer sitting outside the horizon with the perfect instrument can measure everything about the radiation, but still cannot tell that it's thermal, right? But suppose I expand this to an ensemble of identical black holes, each with an observer, a zillion observers, each doing the same experiment, and then cross-comparing. Wouldn't they be able to tell whether or not it's thermal? Or am I just being foolish to assume that such an experimental setup is possible?
So I don't think I have a very sharp answer to that question. I think, as in many of these things, I think the details will matter, right? As I'll see, like you'll see many thought experiments where you'll think, oh, here's an experiment we can do to measure it, and it'll turn out the details will. Yeah. It's similar to the perpetual motion machines. You think, oh yeah, this works, but then there's some micro detail there. So I suspect that there's some detail in that scenario that's going to make a difference. I mean, I suppose so I imagine what you're suggesting is that you're basically doing a kind of state tomography, right, in which you sort of just have a large amount of copies, and then you can just do a tomography experiment and just check, well, here it is. I think there are a couple of papers by Renato Renner and his student where they sort of try and work through a scenario like that, and I think they also identify some barrier, but at this point, I don't think I can tell you clearly what the point was, but I think the details will matter there. Okay, so we're going to deal with precisely these kinds of experiments, which try and isolate some empirical contradiction here. Let me briefly mention a physical aspect of the situation that's going to be relevant for us. And this is what's called the stretched horizon, right? So this is, if you want to hold on to unitarity, and you want to hold on to statistical mechanicalness, then essentially what you'll need is a boundary surface for an exterior field theory that can sort of maintain unitarity, that is, that can absorb and radiate information that reverses that surface. And this boundary surface is the stretched horizon. So this is one Planck length above the true horizon. It's a time-like surface, not null. And it has the entropy, and its location is governed by the fact that it has to have the right entropy, that is the Wittgenstein-Hawking entropy. And one way to think about this is that in the classical limit, it's the membrane paradigm of Thorne, Blanford, MacDonald, and others. So the membrane paradigm was this paradigm that was introduced to try and think of black holes as astrophysical objects. So they found a way to translate the mathematical results in the space-time language into a language in which you can think of a black hole as an object that has a membrane surrounding it and which can carry currents and vibrations and all the stuff that you associate with astrophysical objects. So one way to think about the stretched horizon is a quantization of that. Okay, so let's do a thought experiment. Come on, let's do a thought experiment, which tries and sort of sharpens some of this. Right. So as always, we have two observers, Alice and Bob. Alice is brave. She decides to jump in black hole. Bob is so. I get here. So what from Alice's perspective, we know that if the black hole is large enough, that she's going to experience a smooth crosshead. But from Bob's perspective, the black hole is a unitarily evolving statistical system. And so from his perspective, due to the stretched horizon that I just said, he's going to see Alice as hitting the stretched horizon and essentially just getting dispersed on the stretched horizon. So this seems to be a contradiction. Like it seems like either Alice survives or not, like you can't have both ways. But clearly, from Alice's perspective, she's just fine. From Bob's perspective, Alice means a gruesome death. So you might think, well, here's a contradiction, right? Well, this is there's this picture so far is actually consistent with operational complementarity as described. Because let's see how one might go about for a single observer. So let's say Bob wants to check, did Alice survive or not, right? So how would he do that? He might say, well, look, if Alice crosses the stretched horizon, then maybe she can just send me a message that says, I'm okay, right? But, well, the distance between the stretched horizon and the true horizon is just one Planck length. And so Alice will have to encode her signal in a Planck frequency mode. But this is precisely why, I sort of articulated this restriction on Planck scale physics manipulation, because Alice can't signal to Bob without manipulating Planck scale physics. And you can try and imagine other ways in which they might resolve this apparent inconsistency, but you'll find that all of them will involve some kind of Planck scale phenomena. But we'll come to ways to prove that. So, there's more to be said on this. Okay, so many people don't like operational principles that make reference to observers. Part of this comes from a broader philosophy of science. There's a debate in philosophy of science between realists on the one hand and instrumentalists. Realists take scientific theories as descriptions of the world. Instrumentalists take scientific theories as instruments, as tools for prediction and explanation, but are completely fine with it not actually telling you what the world is like in some deep sense. There's a strong set of arguments within philosophy of science for why instrumentalism has challenges. So I'm not going to rehearse that right now, but perhaps closer to physics, I think a useful and powerful argument to keep in mind here is one due to John Bell. So John Bell, in his famous paper against measurement, sort of makes this joke. He's like, well, look, how long did the universe have to wait for the wave function to collapse? Was like single-celled, did it collapse with a single-celled organism, or did it have to wait for someone with a PhD, right? So the thought there, right, like part of the thought there is that if you're writing down a physical theory which has a field which makes mention of things like observers, then you're facing an explanatory burden, because presumably observers are just constituted by atoms and molecules and the like. So why not just explain the capabilities of observers using the very same physics that you're using to explain everything else? Why do you need an extra principle mentioning them? Shouldn't they just fall out of the theory what they should do? So from that kind of motivation, we might want to come up with a principle of complementarity that doesn't make reference to observers, but instead deals with descriptions of the world or representations of the world. So how would we do this in this context? So there's a very natural strategy here, which one finds in relativity theory, for example, right? So whenever in relativity you find yourself talking about observers, you might just add it, but you don't, and you want to sort of get rid of that talk. A natural thing to do is to trade in talk of observers for talk of reference frames, right? So if you think about the twin paradox, you have Alice standing on Earth, Bob going off and coming back. The reason why that paradox arises is that one confuses names of observers for reference frames. So Bob switches from one inertial frame to a different inertial frame halfway through his journey, but because we still associate reference frames with human names, we think, well, isn't he just one observer? But obviously he's not. So there it's useful to get rid of the observer talk and replace it with reference frame talk. So can we do something similar here, right? Can we get rid of observer talk and replace it with descriptive talk? So the two descriptions that are natural here are one that I'm calling the exterior description, and another is the infalling description. So the exterior description deals with degrees of freedom outside the horizon and has the stretched horizon as the boundary. So this is appropriate for hovering observers, but it's not sort of essentially needs to appeal to them. Similarly, the infalling description is a description that deals with degrees of freedom outside the horizon, but also inside the horizon. This does not have the stretched horizon as a description. So, right, like they're appropriate for those observers, but they're not essential for them. So using this kind of these kinds of descriptions, one might think, well, here's a way of formulating the principle of complementarity. You say that the two descriptions, the exterior and infalling descriptions, are consistent with each other. And the way they're consistent is descriptive. So that is, you can think of them as representing the way the world is with each other and with quantum mechanics. So let's see how this would work here. So in the same scenario, right, one might think that Alice hit the stretched horizon and gets scrambled from the exterior description, and in the infalling description, Alice continues smoothly. And essentially, if you can at least mathematically map the two descriptions to each other, then at the very least, you have the possibility of physical consistency. So what do I mean by that? So, you have, people, so it might be useful just to think in classical general relativity for a second, right? In classical general relativity, from Bob's perspective, Alice gets closer and closer and closer and closer to the horizon, but sort of, he doesn't actually see her make the crossing, so to speak. But from Alice's perspective, she crosses smoothly. But those two ways of describing the situation are equivalent. They're describing the same world, the same physics, in much the same way that you have two different reference frames. And so similarly, in the quantum case, the mathematical constructions will be much more delicate. There have been attempts made by several physicists to try and make such constructions. But at least you can make a mathematical mapping between the story of Alice going into the black hole and the story of Alice hitting the stretched horizon and thermalizing there. Now, there will be philosophical issues here because you might think that, well, how on earth is Alice sort of scrambled on the stretched horizon going to be the same world as one in which she smoothly crosses the horizon? So there's going to be some sort of philosophy of mind problems about how you can map the functional relations between Alice's degrees of freedom to one where she's scrambled on the stretched horizon. But we're not going to get into that, but we just want to flag that, at least mathematically, there's no sort of contradiction here. Yeah, please.
One more question here.
Yeah, please.
So from the point of view of Alice, she is falling in, she crosses the horizon, nothing happens, and she has some history after crossing the horizon. Short-lived, but it exists. Bob has no information on that final piece of Alice's history because it happened behind the horizon. So in your whole argument, you're just looking at Bob's entire reality and Alice's reality until she crosses the horizon. Is that what you're trying to map?
No, even afterwards, right?
Even afterwards, that's the part I'm unclear.
Because what the stretched horizon will have, you can have some dynamics on the stretched horizon. And that dynamics will, at least on this principle, on this way of thinking about things, that those dynamics will somehow encode Alice's story behind the horizon.
Behind the horizon,
Yeah.
okay. So that's the picture here, okay?
Yeah.
Okay.
Siddharth, I don't know if you can hear me.
Reasonable.
Yeah, is that reasonable? I mean, it
Yeah.
seems, the only way I can imagine that is if you're making some kind of holographic argument.
Yeah, this is a kind of holography. I mean, this is, I didn't want to necessarily just, I think in a couple of slides, I literally just say this is kind of holography, but I think because sometimes holographic models have some more details, so I just wanted to flag that the broader picture, but it's a holography, or you can think of it as a kind of holography.
I can hear you, Eric. Can you folks in the BHI hear us?
So I understand the two perspectives outside the horizon, fine, that's all great, I'm totally on board. It's the further step of saying what Ramesh was asking about, in what sense does the outside the horizon conform to the inside the horizon? And that requires some kind of ADS CFT argument, something that's going to tell you that the gravitational bulk is dual to the description on the surface.
Yeah.
So it's really a holographic argument, right? I mean, and not only holographic in general, but it's specifically got to be authorized by some form of duality.
Yeah, I agree with you. So in the rest of the talk, I'll actually argue that there are some very serious problems for this way of thinking about complementarity. But I don't want to minimize the mathematical difficulty of actually constructing this kind of mapping, and they're all conjectural as well. So I just wanted to sort of give the conceptual picture of what is happening here. Did you have a question, Alice?
There's a question on the Zoom.
Yeah.
Eric, do you want to try?
Can you, am I on? Can you hear me?
I can hear you.
Oh, excellent. So I have a kind of follow-up to what Ramesh and Peter were saying, but if you're going to be talking more about this and the problems with the descriptive attitude, then maybe I'll just hold off and wait to see what you have to say before I ask it.
Okay, sounds good. Okay. Yeah.
I have another
Yeah.
sort of, I'm still trying to wrap my head around this, but
Yeah.
so in the Alice picture,
Mhm.
it looks like, so firstly, you're not invoking a stretched horizon there at all, right?
In
So
the
if-
for Alice, yeah.
She's just crossing through and going all the way in.
Yeah.
So in very naively, it looks like you're doing just classical physics,
Mhm.
right? And in Bob's picture, you're trying to say that there's some quantum mechanical system, and you want to put it on the horizon,
Mhm.
or put those whatever information has happened on the horizon. So you're trying to translate the class, what should happen behind the horizon classically into quantum mechanical picture. But shouldn't there be some other, like, shouldn't there be some quantum mechanical stuff happening inside the horizon in Alice's case as well? Would that be missing physics, so to speak?
Yeah, so I think the thought here would be something like, so obviously, what even the classic what is well described by a classical model is still fundamentally quantum mechanical, right? So everything, we're all quantum mechanical, so to speak. So and the thought would be something like the quantum mechanics that's kind of perhaps hidden is maybe not the right word, but at least you don't need, you can construct, okay, here's a more precise way. You can construct good semi-classical models of what's happening when you're using Alice's perspective. Whereas within Bob's perspective, the models that are appropriate will be fully quantum mechanical, but they're still the same physics. I don't know if I have a good analogy here, but essentially, you can have coarse-grained observables or fine-grained observables, and using the coarse-grained observables, you can get a good story that Alice is passing smoothly through across the horizon. But when you use fine-grained observables, then you see the stretched horizon structure more. That would be one way of thinking about it. I'm not yet.
So, I mean, stretched horizon is encoding Alice's experience after she's crossed the
As
horizon.
well, yeah.
Presumably, that's where we think that the semi-classical description is not going to work for Alice eventually too, right?
So
There's a singularity there, we don't know what's.
Oh, yeah. So obviously, right, so part of the whole dialectical structure here, the advantage of that is that we're going to try and restrict the discussion before we get to the singularity. Once we get close to the singularity, all bets are off, right? Everything is Planck scale. So, there'd be dragons and all that, right? Yeah. But yeah, so let me sort of so I think, there are, even before we, please, sorry.
Just one more.
Yeah.
So one way of thinking about it is, if you have some observables or whatever, if you write some things that are on shell, classical on shell, those are the only quantities that you could construct on the stretched horizon that would be described well. So this is the coarse grain sort of. Is that the same way to think about it? Like corrections, if you go off shell, off classical action, then you will not be able to see those degrees of freedom, or you'll not be able to describe them well. Is this an equivalent way of understanding what you're saying?
Yeah, I suppose you can. I think that can make sense. So you're essentially saying you have one solution, which is kind of the dominant semi-classical contribution to the path integral, and that other solutions make quantum corrections essentially, and do the perspective of Alice is perhaps dominated by that contribution, and the stretched horizon and the other. I think that might work. Yeah, I'm not 100% sure, but it seems possible to me. Yeah. Okay, so I think part of the argument that I'm going to make for the rest of this is that I think there are sort of even deeper conceptual problems with this descriptive way of thinking about it that are, or at least that perhaps are fatal, but perhaps at the very least need to be addressed. And so even before we get into the sort of detailed mathematical constructions, it might be worth thinking these through. So here's right. So far, right, like sort of you asked about, what about the dynamics after crossing? I think the sort of another thought along those same lines is to ask, well, presumably Alice is going to show up in the radiation zone, right? She's not going to be confined to the stretched horizon, because if the black hole is evaporating unitarily, then the radiation is going to contain the information constituting Alice. So after the page time, so Alice, quote Alice, that is some scramble of the information constituting her, is going to emerge in the radiation. So this is a little misleading to just say psi, there should be sort of unitary transformations of psi. But that's enough to get you the cloning paradox, right? So now on the infalling description, so this is kind of delicate but important. So remember, right, when we're thinking about descriptive complementarity, we are thinking about descriptions that aren't necessarily indexed to any given observer. So if you think about an infalling description should agree with the exterior description on the exterior, but also contains data about the interior. So on the infalling description, what you'll have is a clone of the initial data, right? So here's why it's really important to make that switch from just thinking about observers to thinking about descriptions. So essentially, so let's say somebody is free falling in the exterior, the description that is sort of generated by that would be the infalling description, and taken as a description, it covers the entire slice, right? So so this then seems that at least on the infalling description, you have a violation of the no. Okay, it's fine. Okay, doesn't like clones. Okay, so on the description, on the infalling description, one sees a cloning of Alice's information. And so if we take our theories as successful representations, that is, if you're thinking in this realist mode, then what you have is a violation of quantum mechanics. And this is inconsistent with descriptive complementarity because it said the descriptions have to be consistent with quantum mechanics. But however, if you switch to the sort of operational way of thinking, the operational complementarity succeeds. So this was primarily sort of really pressed home by this very important work by Hayden and Preskill. And essentially they asked, well, so sustainable relations have similar arguments, but they really sharpened it. So what they asked was, well, how would you operationally verify this clone? Well, here's a natural strategy. So Bob is in the exterior, he collects all the information that's emerging in the radiation. Then okay, so here's the protocol really. So Alice, let's say, carries a qubit with her, she jumps into the black hole. Bob waits in the exterior for the information that Alice has to emerge in the radiation. And then after it emerges, he's going to jump in, and Alice is going to, so once the radiation comes, and then Bob's going to jump in. And then Alice, after she crosses in, is going to send her qubit to Bob, and Bob is going to compare the qubit that he collected from the radiation and the message that he got from Alice and see whether there's a clone, right? And so this seems like operationally you can now check that you had a clone and therefore verify the inconsistency. However, what Hayden and Preskill showed was that Bob won't have enough time to do this even in the most sort of generous scenario you can imagine for Bob. So essentially, Bob will crash into the singularity before he has enough time to verify whether the cloning process actually happened. More precisely, the shortest time that Bob has to acquire the information is O m log m. So essentially, if Alice jumps in after the page time, the information is going to come back out in time O m log m in Planckians. So for a solar mass black hole, that's like 10 to the minus 4 seconds. So whereas on the other hand, this is precisely the longest time Alice can wait before sending to Bob, because if she waits longer, then Bob will hit the singularity. So, so in other words, the time difference will be on the order of Planck time, and so if she has to send the message in time, she'll have to encode it in Planck scale modes. And this is again to emphasize the fact that when stating operational complementarity, we have this restriction that observers can't use Planck scale degrees of freedom. So sort of this is a little bit of a gimmick, but if you think about the score between operational and descriptive complementarity, here we have descriptive complementarity, taking everything as descriptions of the world. You have a straightforward failure, but operationally you can't observe the contradiction. A similar dialectic obtains in the context of the AMS paradox, so this famous quote-unquote firewall paradox, in this paper by Palmieri, Merov, Polchinski, and Sully. And the paradox there was that you have essentially what you imagine is that the black hole is radiating, and if it's following the page curve, what you'll have is that the early radiation will be highly entangled with the late radiation, because that's how the radiation is defined. But at the same time, due to the way in which radiation is produced, you'll have the late radiation being highly entangled with modes across the horizon. But this, if you think of a description on which you have a smooth slice across the horizon, which should be available on the infalling description, then you'll have a violation of entanglement monogamy, and so you'll have a failure of descriptive complementarity. But Harlow and Hayden showed in this famous paper that you can't actually observe this violation of monogamy because in order to do an experiment in which you collect all the radiation, distill that entanglement, and then cross the horizon to check whether it's highly entangled with the modes across the horizon, you'll need to solve a computational task, which will take time exponential in the lifetime of the black hole, and so you won't have enough time to do it essentially. So yeah.
Just a clarifying question. Entanglement monogamy, is that the same as no cloning?
It's a different statement, but they're all like consequences of quantum mechanics.
Right, but there's no question about the truth of that statement, is it? That there is no cloning in quantum mechanics?
Yeah, there's no question about that.
That's.
Yeah, as long as you believe quantum mechanics is linear, it has to be the case.
I see, okay.
Yeah.
Okay.
I mean, the no cloning theorem is simply.
I've never seen the proof, I'm just asking.
I think it's actually fairly straightforward. You just imagine a linear operator, and you imagine if it's linear and you take an arbitrary quantum. So if you have a clone, what that means is that you have a linear operation that takes any given state and produces a copy, and then you can just simply see that because it has to be an arbitrary state, it won't satisfy the linearity. I could probably do it.
Okay,
Yeah.
fine,
Yeah.
okay.
Entangled monogamy, proving that is more delicate. I think that's more involved, but it's still a theorem of the standard quantum mechanics. Yeah. Okay, so I'm last couple of slides. So where do we go? So with this whole story, right? So let's say you're a realist. Actually, and cards on the table, I lean realist myself, even though this talk is kind of friendly to operationalists. So if you're realist, right? Like the initial thought, right? The hope was that the black hole information paradox was kind of like the following paradox, which is, let's say you're on a train and you see a passenger sitting and you're like, oh, that guy's stationary, but somebody on the platform, the train is moving, let's say. Someone on the platform is like, that guy is moving, and when it's on the train, you're like, that guy's stationary. And you're like, oh, that's a paradox, the guy is both moving and stationary. Well, obviously there's no paradox there because you just need to be mindful of what is the relevant reference frame and see that in this frame, it's apt to describe him as moving, and in that frame, it's apt to describe him as sitting still. But so maybe, the initial thought was maybe there's something like that here. Maybe you just need to be careful about descriptions. I think what the cloning paradox and the monogamy violation paradox show is that that's not true. That's not the case. This is a real paradox. So essentially, and there's a real inconsistency in a sense, and so it keeps popping up. You can't. it's a bit of a joke, but it can run, but you can't hack it, right? So essentially, from this perspective, then what you need is a new realist theory, a theory that you can interpret as a description of the world that can explain the paradox. So an analogy here might be, right, like, so let's say you initially, I mean, people knew well before statistical mechanics that perpetual motion machines were not possible, but eventually we got, after more than 100 years, we got to a satisfactory theory that explains why these aren't, well, there are still foundational issues there, but more or less we have a much better understanding of what the world is like, such that it prohibits us from constructing perpetual motion machines. Or, if you're motivated by the quantum measurement problem, you want a story, something like Everettian mechanics or Bohmian mechanics that tell you what the world is like, that leads to, something that looks like collapse in the quantum world. Or if you sort of I mean, this wasn't, obviously, this all happened very close together, but you were sort of remarking by the fact that you got operationally defined simultaneity that's independent of a reference frame. You can think of that as the eventual descriptive theory as just a geometry of space-time that tells you why it is that simultaneity isn't universal. Okay, so that's the kind of program for the realist. But for an operationalist, it's a little bit more sunny. So here's a definition of a paradox, which was given by the philosopher Willard Van Orman Quine. So was at Harvard. And he said a paradox is a plausible argument to an absurd conclusion. So if you're an operationalist, then the conclusion is absurd only if it has operational consequences. So they're like, I don't care about entropy curves. Just tell me some experiment that I can do that leads me to abandon some important bit of physics, right? And if operational complementarity is right, if it's true that you can't, then it'll be true that you can't ever do such an experiment. Obviously, this is a provisional statement. One might come up with a thought experiment tomorrow, which does allow you to directly detect a violation of quantum mechanics in these scenarios. But if operational complementarity is right, whatever experiment you think of, there will always be some barrier, much like for perpetual motion. And so if you're an operationalist and if operational complementarity continues to be successful, then there won't be any paradox. Thank you.
So we have a few minutes for questions.
We should get Eric to ask his question now.
Yeah, he has his hand raised.
Yeah. Eric, go ahead.
Okay, pardon me. Thank you for the talk, Siddharth. That was very comprehensive. I have a few remarks and a couple of questions, and I'll just throw it all out there, and don't try to respond to it all because I don't think there's time, but just choose whatever is most interesting to you. So first remark is of the three premises that you listed at the very beginning, you never actually consider the possibility that the evaporation isn't unitary, and I'm just wondering why, because one might naively expect that since both semi-classical gravity and low energy quantum gravity are effective theories, and we lose unitarity in effective theories all the time without expecting that to tell us anything about anything fundamental about a deeper theory. It's not clear to me why that shouldn't be an option for us to consider. Second question is about the stretched horizon / membrane paradigm. I've never understood how people try and use the stretched horizon in these contexts. It seems to me to be wildly inconsistent. If we really are trying to conceive of the black hole as a quantum statistical mechanical system, then it makes no sense whatsoever to talk about a membrane or horizon, no matter how imaginary, being localized one Planck length away from it. We just can't localize things that way if everything around is quantum mechanical. So I've always been very baffled by the use of the stretched horizon in this context. It actually seems to me to be begging some serious questions. There's it's not clear to me that the Hayden-Kreskel response to the problem with no cloning actually works. because Hayden Preskel's really essentially depends on Bob falling into a singularity. But no one believes that there are going to be singularities when quantum gravity effects take over. But if Bob is falling into a deep quantum gravity regime and not a singularity, then we have no reason to suspect that unitarity is lost and information is lost. So I don't see how Hayden Preskel is supposed to answer that. And finally, in your response to, yeah, just go ahead with that.
No. Do you want to finish?
Yeah, the last one.
No.
The last one was a kind of follow-up to what Ramesh and Peter were talking about the claim that descriptively Alice being scrambled and Alice falling in are have the same mathematical description. You mentioned that that at least from a non-mathematical point of view, this raises problems with philosophy of mind. But I think actually the problem is much more basic. It's a problem of metabolism, not mind. What happens? What happens to our flesh and bones? So I don't think you have to get very fancy pants here to realize that there are some serious physical problems. And I don't think that the analogy with the kind of description that an external observer, as opposed to an infalling observer in a classical black hole spacetime, I don't think that's a good analogy, because those are manifestly not describing the same physics. The external observer does exactly what Ramesh was suggesting. It's dealing with the physics only up until Alice is close to the horizon. Alice's physics is going all the way through. Now, of course, the external observer can predict that what Alice's experience will be, and in that sense can make predictions about what the physics will be once she falls through the horizon. But that's not what the analogy is supposed to be showing. So yeah, that's my qualm about that analogy. Okay. Last thing about the description as an addendum to the issue of mathematical equivalence of different descriptions. I mean, given how serious the problem is, at least I think prima facie, between saying Alice is scrambled, in one description and Alice is perfectly fine in another description, doesn't that suggest that even if that there's something that if you want to be a realist about this, then you shouldn't take the mathematics kind of naively, literally, seriously as a perfect picture of what's happening? So, okay, that's it. Now, really, that's it.
Okay, thank you. Yeah, that was very helpful, and I'll try and answer as many as possible. So taking them in somewhat no particular order. So firstly, yeah, I completely agree that the philosophy of mind was a throwaway remark, I suppose. What I had in mind was some kind of functional relations between the microphysical degrees of freedom in the two pictures, and I just sort of in my mind of functionalism is a concept in philosophy of mind, but the mind part is not essential here. It's simply like how are I agree that how does the kidney function should also be mappable independent of the mind. So yeah, so that was but so I thought just that broad family of problems I associate with the field of philosophy of mind, so that's why I said that. Let's see, what to the question of why not consider rejecting unitarity, I guess I'm not sure I fully understand, because I mean, obviously, right, if you believe that I don't know, like the collapse theories are true or something like that, then this whole discussion is moot, right? Like it doesn't really you're like, well, everything is non-unitary, why? So black hole non-unitarity isn't anything special, but you seem to be suggesting something more specific, that you see violations of unitarity in effective field theories, and I'm not very familiar with that. I thought that we try and recover unitarity there, but even sort of bracketing that, I suppose part of here is that at least there is some fundamental unitary description available here, but maybe we should talk about that offline for me to get clear on.
I agree.
Yeah, and then to the question of the stretched horizon. So your question was, well, how is it mathematically, how is it physically possible? Because how can you have sort of degrees of freedom, you're just sort of hanging out there above the horizon, in a stable way? I think, at least initially, it's a little bit of a, you're kind of folding in what is happening behind the stretched horizon onto the stretched horizon. So you're really thinking in this sort of holographic way. And so and that's why, right, like it's not available for the infalling observer. But again, probably more to be said there. Now, there were a couple of other questions, but I'm actually blanking on them. Do you remember, Helen?
I mean, that's plenty. I don't want to occupy all the Q&A time. And I'll hit you up and make some remarks and replies offline.
Thank you so much. I really appreciate it.
Yeah, there's a question from Colin. Do you want to try speaking? Ron?
Wait, yeah. I would like to ask, regarding the page time paradox. I know it's David Wallace. I understand that he invented this paradox. As far as I understand, people have not yet tried to solve this paradox, unlike the firewall paradox. Do you know whether people try to address this paradox? This is my first question, and the other question is regarding Leonard Susskind. I understand that he's against the firewall resolution, and I would like to know what is his resolution. I mean, I couldn't quite, I was not persuaded by his resolution, by his idea, by his solutions. Instead of the firewall, I mean, there is the firewall, but what does he suggest instead of the firewall? He gives the complementarity, but he's against the firewall. So what does he has instead? What can he get? What can he suggest instead of the firewall? There is the problem here. So these are my two questions regarding the page time paradox and regarding the firewall and Suskind's suggestions. Yeah.
Yeah. So yeah. Let me try and say something to that. So I mean, so the page time paradox, I think, is. So part of the point of my talk is to try and articulate what it is to solve the page time paradox, or what kind of sort of philosophical presuppositions are embedded in attempts to solve this, right? And I think essentially all the sort of work that's been going on, the sort of truckloads of papers that are being written are attempting to solve that paradox. Of course, the most promising recent moves in this game have been the sort of entanglement wedge deconstruction and the islands and all that stuff, which I don't know very much about. But so yeah, I think essentially everything that I've said is in some sense a kind of attempt to solve the page time paradox in one way or the other. They don't call it the page time paradox, that's just a name, but the actual paradox is the one that people have been sort of having in mind in their discussions. And to your second question about the firewall paradox, I mean, so at least the way I have put it here, I suppose the firewall paradox is just a manifestation of the page time paradox. It's, it's just sharpening it.
Yeah, I
And the
know,
reason why it's a sharp,
It's a version of the page time paradox.
yeah, so, and the reason why it's a sharpening is that it seems to suggest some experiment that a single observer could do that might actually bring the paradox into focus. So yeah, so those would be my answers. So I think there's a lot more to be said about both of that.
And we should probably wrap up here as well. So thank you so much.
Thank you. Thank you. Yeah, so if anybody has other questions, please just email me. It's just my first name at fit.edu. Thank you.
Thanks everyone.